thank you for coming. I'm glad to see you here. So we'll be talking about extrapolation in forecasting. But before I start, do you know what M2SL and index from the US have in common with toilet paper? Without the paper thing? All right, I will answer that later. But to start with it, we need to understand what extrapolation is. I don't know your background and so on, so just let's start from the beginning. So, put it simple, it's predicting the unforeseen from some trends or patterns. We have also more fancy definition like people can be divided into two groups, one who can extrapolate from the incomplete data and the other. So why it is important? Imagine you are facing new challenge in life, some issue with no prior knowledge, no prior experience, and you need to tackle it by any means. So what you're gonna do? Well, probably still gonna use your knowledge, still gonna use your experience, but on somewhat different level. Probably you're gonna elevate it somehow, change it, mold it to tackle the challenge. As in business, it's also needed because it helps in some crucial financial decisions, for example, or maybe in risk management. Not this one. Yeah, I have the same problem as before. Yeah, right. So when we have extrapolation, we also have interpolation. And this should be clear for you to see. I'm missing my pointer, so I just can't. But anyway, so if we are going to predict something from the data that is within the historical region, it will be called interpolation. But if you want to go beyond the historical data, it's called extrapolation. Why do we need it? Of course, well, the simplest reason is that population is growing, demand is growing, maybe in not all of the sectors, but in most of them. So whether it's power consumption forecast, raw material demand forecasts, you know, the charts look simple, right? But there is quite a lot of story and noise behind all of them. So we already know that there are some natural extrapolators, right? Like linear extrapolation, which consists of lasso and ridge regression, which might be simple, but are not simplistic. Do not confuse with that. Some of them are very sophisticated. We have also time series methods, but they are more computationally intensive and more complex than the others. Some algorithms typically struggles with the extrapolation, like tree-based algorithms, sometimes neural networks, but we will not dive in neural networks. It's too broad topic for this. We will be focusing on tree-based algorithms here, like decision trees, random forest, or GBM. Well, KNN is also poor at extrapolating, by the way. You might need it sometime. How to overcome extrapolation challenge? One example, time series decomposition. We have the data, we are checking its seasonality, checking its trends, and then we can maybe extrapolate. Using hybrid models or ensemble models, like we can combine any different models, some which are excels at extrapolation, some with excels at interpolation, and combine them by some means. Very helpful is also simple feature engineering, like with lags, moving averages, that helps us catch the trend. So now we will go with real example, but with synthetic data. So it's very laboratory situation. With a simple quadratic function, we can generate the data like follows. This will be region for extrapolation, this will be data for interpolation. Of course, we will not be interpolating data from the training data, right? We are just creating new data from this. But if we know the true function, the result will be almost perfect. So the linear regression with quadratic function underneath will go really good at interpolation and really good at extrapolation. What about decision tree? Well, it kind of struggles at interpolation, but completely fails at extrapolation. Now random trees. Random trees is much better at that interpolation, I mean, from the decision trees, but also fails flat in case of extrapolation. 3 methods together. So, well, simple linear regression excels here. Ensemble model predictions. This will be simple case. We take 2 models, for example, random forest and some linear regression. We are doing training and predictions from both models for all of the data, for interpolation and extrapolation itself. And what we'll do is just to average them. So if we'll have 3 models, we can do the same, right? We can put any number of models to this. Hybrid models predictions might be more sophisticated, but doesn't have to be. So we again are taking 2 models. One will be random forest, for example, and the other will be polynomial regression, for example. And we will use the random forest for the interpolation, but we will train the polynomial regression only on smart portion of the data near the extrapolation region to catch the trend. Then our predictions will be based only on the if statement. So if we know that the data is within the historical data, we will use random forest to predict. If it will go beyond, we will go with polynomial regression. And you see it's quite better than before. So this chart is just summary of everything you've seen. The numbers that we are seeing, the closer to 0, the better. So linear regression at the first place excels at everything. Interpolation, extrapolation, but as I mentioned, that's no surprise because we know the tree function. Decision tree struggles with interpolation a little bit, but it's terrible at extrapolation. Random forest, better than at interpolation, but still terrible at extrapolation, better than decision trees anyway. So then ensemble models quite better, and hybrid also managing. Yeah, but that's what's going with simple data. And when we are dealing with the data, it's mostly not that pretty. It's noisy, it's full of correlation, it's full of additional unused variables and other stuff that's going on, right? So simple models might fail in that. So what alternative do we have? And it's just our alternative. I'm not saying it will be best, but bear with me. I think it's quite nice. So those methods are known for a long time, like tree-based algorithms, neural networks, regression methods, time series networks. But with our approach, we can give some of them, especially tree-based algorithms, new fresh start. It's like we will tell them, do what you are doing the best, but we will give you some boost to that, some wings even. Well, we'll be focusing on standardizing Y variable, but with moving averages. Then, how we choose which one we should take, which window? Well, first, as usual, we are dividing dataset training, validation, and testing. But then comes some catch. In validation, we are making from this one validation sets a lot more validation sets. Like, for example, we are taking 10% of it, or 5, 3, 4, 2, with any step you want. It's still under, it's kind of experimental phase, so it's developing right now. Here is some linear data. This is exactly M2 SL stock. It's money stock. It's used for US government to predict inflation, not inflection, but inflation, yes, right? For example, here is some global trend without using this region will be forecasting. And yeah, when we are not using any standardization methods, the random trees algorithm is going like that. right? It was flat, you already saw it from the simple data as well. But with our approach, we can go slightly better. When I mentioned you about these validation steps, we need to check the window that we need to standardize. Use for standardization, I'm sorry. But we have many windows. We can choose any number of windows that we want to test. But then again, to choose the optimal one, we need some measure. We went with Manhattan distance. It doesn't have to be Manhattan distance, other are better, but yeah, Euclidean also will be fine. So for not this slide, sorry guys, I think it's the same as before. Yeah, so we have some validation steps here. Now, from each validation step, we had some optimal window. So because they are different, we want to average it somehow, or we'll just took the average and the median value from this. The same picture, but with closer on its last part of it. So here is some summary table, graphical results. When you are looking at the -1 minus W IPE, we want to have the closer to 1, the better. That's the interpretation. So when we are using our method, this here is called inverted row is as the, without standardizing the values, we received much better results than the before. You don't have to bother with other metrics. They were also better, but might be less informative. Now, this toilet paper I mentioned before, right? So I don't know if it revealed to you already what's going on and why it's related, but well, we'll be predicting this region as well. And yeah, those raw predictions, and this is our approach. So now when you see at the table, results are still better, but they are not that spectacular as before. Well, partially because the data here is quite noisy. There are a lot of outliers. I didn't get rid of them to make it a challenge. But anyway, it's still better. And this one, so we already are doing some big scale data analysis, especially with Cloudera. We are able to run like even for 6,000 and 5,000 stores with 5,000 products, even 10,000 thousands of models, AI agents, in a scaled environment. It was quite nice. So what is the take from this? Well, this is kind of new method because I was going through the literature. There were some examples, some mentions about something similar, but I didn't see it really tested. So this method that I was talking about to you is about giving wings to methods that previously couldn't extrapolate, like tree-based algorithms. So, as I mentioned, we are asking them to do the same thing that they excel on. Please interpolate. We are giving you boosting by doing good standardization. So thank you for your attention, and please came to our stall that before the room. There are pretty nice prizes for the quizzes, and I hope you enjoy it. Thank you.
All right, thank you, Mateusz, for a very insightful presentation. Do we have any questions?
I have a question regarding do you have any information how your results compare to other solutions related to time series prediction, like, for example, TimesFM from Google?
Do you mean looking for the trends, for example, and so on, like ARIMA models? And
yeah, I just wanted to know if you compared your solution with other options.
Well, those options are not bad by themselves. And cannot give you a clear answer because we are doing this with my colleagues. We were comparing, of course, with others, and they were also quite good. But it's just more simplistic in implementation and in production.
Okay, thank you.